Good morning, I'm Dick Trudgeon from the CW Math Department here at Central. I'm also the liaison for the Cornerstone program for college and high school credit. And I get to do a couple of these sections too. I'm going to do, in our book, it happens to come fairly late in our pre-calc course, but in your course it may come at any time, so we're just kind of mixing these things up as they go. My subject today is law of sines and law of cosines. One of the most applicable things that you're going to run into when you are doing anything with trigonometry. Alright, so we start here and we're looking at law of sines and law of cosines. There's a few things that you need to remember. Number one, SOHCAHTOA only works in right triangles. I can't tell you how many times I have seen students try to use that in a triangle that wasn't a right triangle. It only works in a right triangle. There's no hypotenuse in this triangle here. No matter how much you try to believe it, there isn't one, so you can't use it. The Pythagorean theorem only works in right triangles. It is not something that works in just any triangle. So we've got to make sure that you don't think about using that either. Some triangle reminders that we have. And these sound pretty elementary, but they're the things that trip students up more than anything else. Some of the lengths of the two shorter sides has to be more than the length of the long side. Not equal to or greater, it has to be greater. Otherwise, you could take a crooked path and get somewhere as fast as if you took the straight path. And my mama told me that doesn't work. So we got to make sure that we take and check our triangle to make sure that the one that we've produced actually does what we say it's going to do. Angles must add up to exactly 180 degrees. Now you would be surprised, but this is the thing that trips students up the most. Because they take and they'll work the angles out in a couple of different directions and they'll get great answers, but when you add up the angles, they don't equal 180 degrees. So we've got to check that out. And finally, it has to make sense that the longest side would be opposite the largest angle. The shortest side opposite the smallest angle. Now that automatically makes the medium side opposite the medium-sized angle, so we're good there. All right, a little warning here. I never really liked checking my work when I was in your seat either. I always thought, if I do a good job the first time, I know that it's going to be pretty right most of the time. But checking our work here isn't just to check our arithmetic. We need to check out those things we just mentioned. And we also have some other things to think about. Sometimes your given information won't even lead you to a right triangle or to a triangle of any kind. Sometimes you'll get two solutions that work and you need to make sure that you found both of them. And sometimes you get one solution that works and one that didn't. So we need to always make sure that we check those things out. Other must-haves in order to use law of sines and law of cosines. You got to have at least 3 given pieces of information. It has to include at least one side. If we take a look at this triangle here, you can't do anything with it. You can't apply something without having a third piece of information there. There is no Pythagorean theorem in a triangle that's not a right triangle. This particular one here has 3 pieces of information, but it doesn't have a side. You must have at least one side of the triangle. So we look at law of cosines. Now, law of cosines, it's pretty easy to look at. You're used to probably, doing your Pythagorean theorem in terms of a squared plus b squared equals c squared. So we'll start out with c squared equals. That seems to be the most common one that we run into. Notice, if you will, as we take a look at things here, that the letters that we start out with here, which is a C, and the letter at the end, which is also a capital C for an angle, are the same. The letters in the middle are the other two. It's always in this form. If we're looking for B, then it's B squared at the front and capital B at the end. If we're looking for A, it's A squared at the front and capital A at the end. So the pattern, a lot of students just memorize it one way and then you can just change it with the others because the pattern's pretty easy to follow. When we're going to use law of cosines, one of those places is what I call an angle sandwich, where we've got an angle that's in between two sides. That's an automatic that tells us that it's a good time to use law of cosines. The other time that's good to use law of cosines is when you have three sides. See, we had to have three pieces of information. It never said we had to have an angle, but it said we had to have at least one side and three pieces of information. So these are the times that we're going to use law of cosines. All right, things to watch out for. Not a whole lot with law of cosines, but maybe the first one is right there. You see that little squared on the C? It's very normal that we're going to put things into our calculators. We're going to go a squared plus b squared minus 2ab cosine angle C. But then we have to remember to take the square root at the final step. If you happen to be looking for the angle, maybe you knew what side C, side A, and side B were, and you were looking for angle C. You always have to remember the last step in any problem when you're looking for an angle like this is using inverse. We have to use inverse. Don't forget to see if your answers make sense. We've talked about that already. Now, I think it's a good habit for you to get into the point where you round to final answer only. I certainly wouldn't figure out what cosine of C was to 4 decimals, round that to 2, and then do the same thing with A and B, and then square and round again. Best thing after you've taken the square root at the end is the time to take and round your answer. And be in degree mode. Before you got to pre-calculus, you were probably always in degree mode. You probably didn't even talk about radians. When you get to calculus, you'll be in radian mode almost all the time. But here in pre-calc, we go back and forth. If we're graphing a sine curve, we may be in radian mode, and now we're doing triangle problems again. We need to be in degree mode. So I would always check that thing out before you did any sort of calculations with it at all. All right, let's take a look at one with an angle sandwich. Now we've got this labeled here. I didn't bother to label all the vertices since we're just setting it up to solve for one particular thing this time. So we've got the triangle set up. We've got the angle sandwiched in between the two sides, so we know that's law of cosines. My suggestion to you is put the whole thing in your calculator at once. Put the whole thing in there at once and see what you come up with. Okay? So take and do that now and find out if you're going to get the same answer that we get in just a second. Okay, if you've done that and you've got everything in your calculator and then you took the square root of the answer when you got done, you should have come up with a missing side that rounds to the nearest hundredth at 6.26. Now, once you have that missing side, you won't need to use the law of cosines again in this problem. You could, but usually it's easier to use the law of sines, which we will get into in just a few minutes. Let's look at the other example. And we're going to do a whole set of some application things in another section when we get done with this. The other section, or the other example here, would be the one where you have three sides. Now, of course, you need to label your vertices here. I think that's going to be important. And then it is your choice, but I'm going to give you a hint that's going to say find the biggest angle first. Now, there are times in a textbook that they will say, here's the labeling, find angle A. And if it's not the biggest angle first, then do what they tell you to do. But if you have your choice and you're just asked to solve the triangle, I would tell you to find the biggest angle first, because that usually avoids some problems with law of sines when you get down to it. At least lets you see what's going on a little easier. Okay, when we do this, and we've labeled the triangle, and I happen to have labeled C opposite the longest side of 14. So since C is the biggest angle, we're going to solve for that. So we're going to use the form that has that. C squared equals A squared plus B squared minus 2AB cosine C. Nice thing about law of cosines is, you know, the order I put things in doesn't matter a whole lot because A and B are the only things I know, and when I put them in there, it doesn't matter whether it's A squared B plus B squared or B squared plus A squared. When you're going straight towards the side this time, you can kind of get things in. There's only one place to put things. So we can put that. But this time, we're looking for an angle. So we've got to somehow take, and somehow isolate this cosine over here. Let's see, the highlighter, see if I can get that highlighted. This thing has to get by itself. We have to get cosine C by itself. So probably the easiest thing to do there is to just go through algebraically. I don't like to plug all the numbers in and then have something dependent on whether I put them in right. I like to look and see for a pattern, see if I can find one. So I'm going to take and subtract a squared from both sides and subtract b squared from both sides. Because I know when I undo equations, first I undo addition and subtraction. So I undo the addition of those two things by subtracting them from both sides. And then after that, I will take and divide both sides by negative 2ab. Now you notice that I put parentheses around there, because I'm going to put this in my calculator. And when I do, anytime I've got more than one thing on the top or bottom of a fraction, I like to take and make sure that I put parentheses around the whole thing so the calculator does the order of operations right. So again, this is something you could memorize. I'm looking for C, so it still starts with a C at the beginning, C squared minus the other 2 squared, and then the division by minus 2ab. So if we do that, we got to make sure we're looking for an angle. As I said before, the final step has got to be inverse of that in order to find the angle. So then we're going to take, and we've got inverse coming at the very end step. All right, so once again, try that in your classroom, see what you're going to get for angle C. Okay, if you've done this, and if I haven't made a mistake along the line somewhere, maybe you've got some agreement at 74.8 degrees. Now I have a tendency, whenever I can, to round sides to the nearest hundredth and angles to the nearest tenth. You need to do it the way your instructor says to do it, except at the final exam, which I make up, then I'll tell you how I want you to round answers on that, and you can do that. But I think it's good that you're going to have some sort of a general idea of how you're going to round things. As I mentioned before, we usually don't have to use law of cosines more than once. Now there certainly would be no reason to use it here to find side C, because we already have that. But other people might think, okay, I'd like to use that again. But normally we'll go to law of sines after that point. Now, after we discuss law of sines, I'll give you a link to the proof of the law of cosines. I don't ever like to believe that we just pulled something out of a hat somewhere and that, oh, here's another formula for us to memorize. I think it's a good idea to take and be able to look at things and see where they came from. And so I'll point that out. We'll look at the law of sines first, then we'll look at the proofs of those in a little bit. So, law of sines. We have to have at least one side and its opposite angle. Of course, we still need that 3 givens that I said is an absolute must that we must have every time. So if we look at this thing here, we can use the law of sines here because we have a side of 40 and the angle opposite that of 20. As long as we have just one pair of those and some third piece of information, we can use the law of sines. Now, a lot of people would look at this one and think, oh, well, Pythagorean theorem can be used here. It's a right triangle. No, it's not a right triangle unless you're told that that's a 90-degree angle. Don't ever assume it looks like it's a right triangle, therefore I'm going to work on it as a right triangle. You can't do that. Okay? So here again, we have to be given at least one side and its opposite angle. Do you think you could do this one? Well, if you remember that the angles in the triangle add up to 180 degrees, then you could have that angle there at 120, and because you have that angle of 120 opposite the side of 80, then you can do it. You can actually use the law of sines. All right. How about this one? I don't think we can find another angle. Talk for a second about how you might be able to solve this one. Okay. Hopefully you recognized you can use the law of cosines there because you do have a angle sandwich that you can work with. All right, so we're still in this given thing as we look at here. Starting to use the law of sines. With law of cosines, if you were looking for a side, labeling it wasn't as critical as it is now. When you're using law of sines, you need to start out with labeling your triangle. So if you've got a triangle like this where we started and we did have a side opposite an angle, then we start by doing some labeling on there. You can label it any way you want to. If the book labels it that you're using a certain way, then you need to label it the same way as that. But other than that, you can work around it a little bit. So you can use the law of sines here because you've got a 40 and the angle opposite of 20. The law of sines always looks exactly the same. Now I have seen some books that put the sides on the top, little a over sine A, little b over sine B, little c over sine C. However you do that is fine, as long as the ratios are looking the same as you go through from one to another. The sine of angle A divided by the length of side A is exactly the same as the sine of angle B divided by the length of side B is also the same as the sine of angle C divided by the length of side C. Now here's one of the proofs that we're talking about there. There's a link to that online proof of the law of sines. Now this particular one is done by one of the teachers at Khan Academy, which some of you may have visited for some tutorial help along the way. And I thought, yeah, I can do that here and extend this time out a little bit, but I would do basically the same thing as they did. I might do a little bit better, but it's going to be the same steps that they follow through. And so I thought, why reinvent that? Why not just give you an opportunity? Your class can go and look at this all at once if you want to. You can do that the way you want. But if you look at that particular link right there, that will take you to a proof of the law of sines that comes out pretty nicely. All right, let's apply this to a problem that we have. We go back to the one that we had a few minutes ago. And in this particular problem, we had angle A and side A. So we'll be able to put those numbers in where they need to go. And we also have side B. And that's about all we had to start out with. So when we set it up, it looked like sine 20 degrees divided by the length of 40 is sine of angle B divided by the length of 50. And then we got that sine C over little c over there on the right side, which doesn't do us a whole lot of good right now. If you're going to solve a proportion, you can only solve it with 4 things if you've got 3 of them. So it would make most sense to use the first 2 ratios because there's only one unknown, and that's angle B. It wouldn't make sense to use the second and third or the first and third because there's too many things we wouldn't know. So if we set those things up to cross multiply, I want you to look at the way I set it up. I don't set it up sine 20 degrees times 50 because then I've got to either insert parentheses or I have to insert a multiplication sign. And if I forgot to do that, I might have 20 times 50 for my angle instead of that. Most of your calculators now, when you press sine, they put in a parentheses before the 20 degrees, so you'll have to close that out. So I've got 50 sine 20 equals 40 sine B. And I always tell myself here that I'm looking for an angle if it's a capital letter. So when I do this multiplication and division, my last step is always going to be inverse. Not inverse cosine, because we're using sine, but inverse sine this time. So you go ahead and solve this and see what you come up with for angle B. All right, if we've all done things pretty much the same and gone to the nearest tenth, we now have B is equal to 25.3 degrees. Okay, so if we subtract from 180, we should be able to get the length of, the size of angle C to be 134.7. I'll try to squeeze that in there just a little bit. So now we have more information that we had before, and like I said, we don't usually use law of cosines more than once in a problem, but law of sines often gets used more than once. So let's reset that up. We've got The same information we had before, but with new things filled in too. Now we can solve for side C. Won't be any inverse this time because we're looking for a side. Now I would take and pick the first ratio and the last one. 25.3 was a rounded answer, so I think, why do I want to use a rounded answer in my problem to solve for another one? So I'll set up my proportion with the first fraction and the third fraction. So neglecting to write the middle one for now, we have another problem that we can take and figure out the side that's going on there, and we can see what's going on. So we're going to take and solve that. So let's go on here to this and see where we were. Let's set it up now. 40 sine 134.7 equals C sine 20. Now I've gotten myself to a shortcut that I'm always trying to use. I always look and see where is this diagonal where I know both things. That particular diagonal right there, I know both things on that diagonal when I cross multiply. And then there's one more piece of information here that I have, and that's this one here. So I always end up saying, you know what I'm going to do? I'm going to multiply the two things on the diagonal that I know, 40 sine 37, and divide by the other piece of information. So when I solve this, I'm going to take 40 sine 134.7 divided by sine 20. There will be no inverse. If you solve that for C, we should get about 83.13. Now, checking things out. I think that's, super important for us. The two smaller sides are 40 and 50. That's more than 83.13 when you add them together, so that's good. The angles do add up to 180 degrees. That's good. And you can see that the largest angle C is opposite the longest side, little c, and the smallest angle A is opposite the smallest side of 40. So it looks like we have a workable solution. Now, I warned you about checking things out. And I think there's a reason for that you need to see in terms of what goes on here. Okay? If we take a look at this thing, it's a little blurry, I understand that. But if anybody in here doesn't recognize the sine curve as the red one, then we're in a little trouble anyway. So if we look at that red curve and we see where the green arrow comes in there at pi, we notice that there are two places between 0 and 180 degrees, pi radians. There are two places that have the same sign. There are two places. One of them is right there for this particular value, and one of them is right there where the black line intersects. So when we have just solved for an angle using inverse sine, there might be more than one place that satisfies the problem. There are two angles between 0 and 180 degrees. If you remember how you found them, if you knew one of them, you subtracted it from 180 degrees to get the other possibility. Notice this is not the case with cosine. Cosine does have two places that it repeats itself with the same value for cosine, but it's not in that same domain of 0 to 180 degrees over this way. It's over here, it's 360 minus theta instead of 180 minus theta. So, we've got that. So when we solve for using the law of sines, there might be, and that is a big might there, another angle that might also lead to a viable solution. So let's see what happened with the one we just did. We just solved, and all the numbers that are put in there were ones that we were either given or came up with. But the only ones we were given for sure was the 50, the 40, and the 20 degrees. We solved for the 25.3 degrees. But now if we look at this, we see that we had found B was 25.3 degrees. But we know now that B could possibly be might be, maybe, have another value of 154.7. And if it did, that would still leave enough degrees for angle C. Angle C would no longer be the biggest angle, but it would still leave enough degrees. So you can't say, well, yeah, we put a 154.7 and leave the 134.7 here. No, that's not going to work. That's not going to work. Okay? So let's see if this could be possible. Let's find out if that could work. If angle B was actually 154.7 instead of 25.3, and we subtracted from 180 degrees, we'd have a new value for angle C. And it looks like the angles add up to 180, so that part of the check is okay. Then I'll set up the law of sines and see what we get for C this time. Sine of 20 over 40 equals sine of 5.3 over little c. Set up the cross, ready to cross multiply, and we should get an answer of 10.80. Now certainly at any time, instructors feel free to stop the video and work out things and make sure that everybody's doing it right. There's no speed involved here, but you need to take it at the pace that works for your classroom. So we've got an angle of 10.80. Well, let's check that out again. See if things check out the way you want it to be. Do we have the two smaller sides adding up to more than the large side? Do we have the smallest angle opposite the smallest side and the biggest angle opposite the biggest side? If we do, then we actually have two different triangles that are viable solutions in this particular problem. So let's see whether we might get two answers here or not. Talk about that for a minute. Well, I hope you came up with the answer of no, because of the fact that that third angle is set in size. It has a size found by subtracting from 180, but there's only one possibility there because you were given the other two angles. How about in this one? What could happen here? Well, I hope you came up with maybe. That's usually where you want to start. You either start with no or you start with maybe. And in this case, we have to start with maybe and see and go ahead and set it up and see what starts to happen. Sine of 40 over 3 equals sine of c over 2. All right, so then we take a look and we get an answer from that of 25.4 degrees. And when we get 25.4 degrees, that gives us a solution of angle B is equal to 114.6. And that looks good so far. At least we got three angles and they add up to 180 degrees. We would still have to solve for little b and see if we have a triangle that all parts check out in. But we want to think at the same time, all right, now is there another possibility for angle C? We solved and got 25.4. Is it possible for angle C to be 154.6? Think about that for a minute in terms of what that would leave for angle B if angle C was 154.6. Okay, what did you determine from that? Well, if you had 154.6 and 40 degrees, looks like that would have been too many. So how about this one? Again, maybe. Might have one solution, might have two. Let's find out what happens. Sine of 40 over 1 equals sine of c over 2. Well, that's the only way I could set it up because that third piece of information was side c. So then I set up 2 sine 40 equals sine c. And so before I do my inverse, I go ahead and figure out what 2 sine 40 is, and I get 1.2856. Is this a problem? It's a big problem. You learned that sine doesn't get any bigger than 1 or any smaller than -1. So to come up with a sine that's bigger than 1 is going to give you some sort of error in your calculator if you try to do it. Sometimes we said there are no triangles that work, so that was a big problem in this case. Okay, I promised you that there would be a proof of the law of cosines too. So here's a link to another Khan Academy proof of the law of cosines. So you can go through there and you can see where it actually came from. So feel free to stop the video now and do that if your instructor wants you to do that. All right, some other basic things that come out as we're talking about triangles, and we're going to get into vectors in another lesson pretty soon, is the concept of bearings. Bearings may be given as the number of degrees clockwise from due north. Okay? So we could have a bearing listed here as coming from due north to there. That could be one way that we give a bearing. That's one possibility. In aeronautics, that's probably the most common possibility that we're going to have. Let's say 225 degrees. I tried to make that little arrow as close to the splitting that quadrant in half as I could, which would be 225 degrees. That's one way that we can do bearings. Another way that bearings are sometimes done is the number of degrees west or east of either north or south. That's a mouthful right there. Good. It's either west or east of north or south. Well, it's not that hard to figure out. Whichever is closer, meaning this is closer to south than it is to north. This particular arrow right here is closer to south than it is to north. And from the south, it is certainly west of there. So we could list that, instead of going all the way from north around, just list it from south. And we would read that south, 45 degrees west. It is not read west 45 degrees south. It always starts out with a letter that in terms of where are you coming from, and because we were coming from the south, and which direction from the south are you going? You're going to the west. Okay, let's go back to that for just a second. All right, so that's another way that could be. Since I split that quadrant in half, it would be south 45 degrees west. I know some of the older books still talk about you are 45 degrees west of south. Well, that's good nomenclature too. The only difference is we've eliminated the word of by putting a comma in there instead. Okay, math angles. When we deal with math, we have always taken and done our angles counterclockwise from the right. We've always gone this way. Counterclockwise from due right. That's why this first quadrant up here was called quadrant 1. This one up here was quadrant 1. And then 2, 3, 4. We took and we looked at those things in terms of counterclockwise. So that particular direction there could be listed in about 3 ways. One, you might list it as a math angle of 300 degrees. Now, I tried to make that about 30 degrees to the east of the south there. So you can take a look, it's about a third of that quadrant there. So you could list it as 270 plus 30 is 300 degrees as a math angle. You could list it from the south, a bearing of south 30 degrees to the east. Or you could say it's a bearing of 150 degrees. Where did that 150 came from? Well, it came from taking 90 here plus 60 more to there. So as a bearing of 150 degrees. Here's another example. If we wanted to list it as a math angle, we could say here's a math angle of 150 degrees. Because we've gone through 3 quadrants. No. In a math angle, we take and go counterclockwise. It's really important to remember. We've gone through 1 quadrant in 60 degrees more for 150 degrees. We could take it from the north. We've got a bearing of north, 60 degrees to the west, or the 300 degrees would be now we're going clockwise from north. And if we go clockwise from north, we're going 270 and 30 more is 300 degrees. So we have basically one more thing to cover in this section. We're going to have some application problems that I'm doing separately here. But just to get the information, we have to go back and talk about triangle area a little bit. When you were studying right triangle applications, you probably started out with area equals base times height. And as long as you had a perpendicular height and you could figure out the length of the base and the height, that's what you went with. And then you learned that if you could extend that to any triangle, you took it to 1/2 length A times length B times the sine of the angle in between them. Now we could say 1/2 AB sine C in this case, because angle C is always the one that's in between sides A and B because it's opposite of side C. But if you knew two sides and the angle in between them, you had an easy formula for figuring out the area. Now if you didn't know all those pieces, you could find those pieces using the law of sines and law of cosines that we've been dealing with. And as soon as you found two sides and the angle in between, you would be ready to use that formula right there. However, there's one more way that you can find the area of a triangle. When you don't have any angles, rather than go back and try to find it using law of cosines, rather than doing that, which would be slower, it would be quicker to apply what's called Heron's formula. Now some books actually call it Hero's formula. So I've seen it both ways, so whichever way your book does is fine. But it says if you've got 3 sides and no angles, rather than go through solving the triangle to find one of the angles, you can go through these steps here. Find the perimeter of the triangle and take 1/2 of that number. Perimeter, you walked yourself around the triangle. You had all 3 sides, so that'd be a little addition problem. And then you take 1/2 of that, and we're going to call that S. S stands for the semi-perimeter. And of course the triangle has sides A, B, and C. So then our formula for area looks like this. We take the square root of this product of 4 numbers, the semi-perimeter S, times what you get when you subtract one of the sides from it, what you get when you subtract the second side from it, and what you get when you subtract the third side from it. When you get done with that, you will have the area of any triangle. Now, I didn't take and put this in terms of a lot of problems yet. I assume that when your instructors are going through this, that they're going to take and go as slow as you need to and stop it whenever you need to in order to come up with this. But where I am going to take and work out some very specific application problems to the use of law of sines and law of cosines in the next section of our video. Thank you.